Welcome to CSEGuru. In this session, we will discuss Bellman-Ford algorithm and dynamic programming technique. Bellman-Ford algorithm is used to solve single source shortest path problem. So, single source shortest path problem is nothing but it is used to find the shortest path from the source vertex to all other vertices in the given weighted connected graph. The same single source shortest path problem can be solved using the famous algorithm, that is Dijikra's algorithm. Already we have discussed about Dijikra's algorithm and we have solved the problems also. I will provide the link in the description for your reference. The Dijikra's algorithm is also used to find the shortest path from the source vertex to all other vertices. Bellman-Ford algorithm is also the same purpose only. But what is the drawback in Dijikra's algorithm in the sense? This Dijikra's algorithm will work only for the edges with positive weights. Okay, suppose if the edges contains negative weights in the sense, this Dijikra's algorithm may not give correct result. So to overcome this drawback, we will use the Bellman-Ford algorithm. This Bellman-Ford algorithm will work for the edges with negative weights also. It will work for both positive weights as well as negative weights. But Dijikra's algorithm will not work for edges with negative weights. Okay. So now we will discuss one problem to implement a Bellman-Ford algorithm. This is the given graph. We need to find the shortest path from node 1. So this node 1 will be considered as the source vertex. So from node 1 to all other vertices, what is the shortest path we need to find using Bellman-Ford algorithm. Two key points we need to note down in Bellman-Ford algorithm. First one is we are going to relax the edges in Bellman-Ford algorithm n minus 1 times. Okay. So here n is nothing but the number of vertices in the given graph. So for example, in our given graph, there are 7 vertices. So 7 minus 1, that is 6 times we are going to relax the edges in Bellman-Ford algorithm for this given graph. So here we are going to implement 6 iterations. There is a meaning. Okay. And second thing, if you are considering in the sense, suppose if you want to find the distance between 2 and 5 in the sense, this is the starting vertex. That is the source vertex and this is the destination vertex in the sense. Consider this is vertex U and this is vertex V. Okay. So distance of vertex 2 is D of U. The distance of vertex V is D of V. Suppose while relaxing the edges. So relaxing the edges means every iteration we are going to find the shortest path for each edge. Suppose if the edge is having already shortest path in the sense, it's okay. But we are going to try with the new path in every iteration and suppose that cost is minimum in the sense, we will consider the minimum cost. Okay. So the relaxing the edges means every iteration we are going to find the new path for each vertex. And suppose if that is minimum in the sense, we will consider that cost. If you are going to implement a new path from U to V in the sense, how we are going to implement in the sense, distance of V is minimum of the distance of V. Suppose if distance is already minimum in the sense, we will consider this one, or otherwise through this vertex, if you are getting a minimum path, we will consider that one. Okay. So through this vertex in the sense, that is D of U plus what is the cost to travel from 2 to 5? That is here minus 1. Okay. This cost we need to include. So D of U plus cost of U comma V we will consider. Which one is minimum, that we will consider the distance for this vertex. Okay. So these two key points we need to remember for every iteration while relaxing the edges. So consider the first iteration. First step, we are going to find the initial cost matrix for this given graph. So in the problem itself, they have given source vertex as 1. So we will consider the source vertex 1. And the first time we are going to relax in the edges. So here relaxing the edges means for each vertex, what is the distance we are going to find. Okay. So since this is the first iteration, we are going to implement directly what is the cost. So that we will implement in a cost adjacency matrix. So since the source vertex is 1, consider from 1. So consider the adjacency matrix with the number of vertices, that is 7 in the row wise as well as column wise. So if you are considering here in adjacency matrix, 1 to 1 there is no path, 2 to 2 there is no path, 3 to 3, 4 to 4 likewise, vertex to itself there may not be a path here. Okay, so we will consider that distance will be 0. So 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6, 7 to 7, all it will be 0, 1. Next up, so from the vertex 1, what is the distance to other vertex? That is a direct path that we will consider first. So 1 to 2, that is a direct path and its distance is 6. So 1 to 2, distance is 6. Similarly, 1 to 3, distance is 5. And 1 to 4, distance is 5. Okay. And if you are considering the vertices 5, 6 and 7, there is no direct path from vertex 1. Okay. So we don't know the distance. So we will consider it as infinite. Similarly, we will implement for vertex 2 to 7. So from 2, if you are considering, there is only one direct path from 2 to 5. That is -1. And the remaining all other vertices, there is no direct path. We don't know the distance. So consider it as infinite. Okay. Similarly, vertex 3, if you are considering in this, there is a direct path from 3 to 2 and 3 to 5. So 3 to 2, distance is -2. And 3 to 5, distance is 1. For the remaining vertices, we don't know the distance. There is no direct path. So we will implement as infinite. Next, vertex 4, if you are considering in this sense, there are two direct paths from 4 to 3 and 4 to 6. So 4 to 3, distance is -2. And 4 to 6, distance is -1. And the remaining vertices, we don't know the distance. So, infinite. Similarly, vertex 5, only one direct path, 5 to 7, distance is 3. Remaining vertices, we don't know the distance. So, it is infinite. Vertex 6, if you are considering, only one direct path from 6 to 7, distance is 3. And the remaining vertices, distance, we don't know. It is infinite. Similarly, 7, if you are considering, there is no direct path from vertex 7 to any other vertices. So, everything we will make it as infinite. So this is the initial cost adjacency matrix by considering the source vertex 1. So from this initial cost adjacency matrix, we come to know from the source vertex to all other vertices, this is the corresponding shortest path according to first iteration. Okay. So this first row we will consider as initial distance. That is the initial shortest path. Then with this initial shortest path, we are going to add the corresponding cost matrix excluding the source vertex. Since we are not going to find the shortest path from source vertex 1 to itself, we are not going to find it. Okay. From the source vertex to all other vertices only, we are going to find the shortest path. So consider the cost matrix excluding the source vertex. Okay. So add this initial shortest distance with this corresponding cost matrix value, then we will get a new cost matrix. So from that cost matrix, which is the minimum value we will consider as the shortest path in that particular iteration. Okay. And with that shortest path, continue the next iteration, the same procedure. So this procedure continues for every iteration, that is relaxing the edges. N-1 times we will continue this procedure. And finally, we will get a shortest path from source vertex to all other vertices in the given graph. Now, we will continue the next iteration with this initial shortest path. So, this is the initial shortest path what we got in previous iteration. And this is the cost matrix for the vertices 2, 3, 4, 5, 6 and 7 excluding vertex 1. So now add this initial distance with this corresponding cost matrix value, we will get a new cost matrix. So this is relaxing the edges k equal to 2. Okay. So 0 plus 6, we will get it as 6. 0 plus 5, we will get it as 5. Again 0 plus 5. That is corresponding values we have to add and place it in the cost. So 0 plus 5, it is 5. 0 plus infinite, infinite. Similarly, second row, 6 plus this corresponding values. So 6 plus 0, 6. 6 plus infinite. Again 6 plus infinite. 6 minus 1 is 5. 6 plus infinite. 6 plus infinite. Next 5 minus 2, 3. 5 plus 0. Then 5 plus infinite. 5 plus 1, 6. 5 plus infinite. 5 plus infinite. Next row, 5 plus this corresponding values. So 5 plus infinite, 5 minus 2, 3, 5 plus 0, 5, 5 plus infinite, 5 minus 1, 4, 5 plus infinite. Next, With infinite, all we will get infinite values only for all these three rows. Okay, so all we will get infinite. So this is the new cost matrix we got by adding the initial distance with the corresponding cost matrix. So from this new cost matrix values and already the shortest distance value for vertex 2, which one is minimum, that we will consider now. So among this one, which one is minimum? 3 is minimum. Next, for vertex 3, 3 is minimum. For vertex 4, 5 is minimum. For vertex 5, again 5 is minimum. For vertex 6, 4 is minimum. For vertex 7, there is no value, so infinite. So this is the new shortest distance we got from source vertex to all other vertices by relaxing the edges k equal to 2. And this is the second iteration. With this shortest distance, implement the same procedure for next iteration. So this is the new shortest path from source vertex to all other vertices we got in previous iteration. Now, with this shortest path, add with the corresponding cost matrix values, we will get a new cost matrix. So from that new cost matrix, find the minimum cost. Next, that will be the new shortest distance. So with that, continue the next iteration. So this procedure continues for n minus 1 times. That is nothing but relaxing the edges. Okay. So now with this shortest distance, add the corresponding cost matrix value to get the new cost matrix. So 0 plus 6, 6, 0 plus 5, 0 plus 5, 0 plus infinite, infinite. Okay. Next for vertex 2, 3 plus 0, 3 plus infinite, 3 minus 1, 2, 3 plus infinite, 3 plus infinite. Next for vertex 3, 3 minus 2, 1, 3 plus 0, 3, 3 plus infinite, 3 plus 1, 4, 3 plus infinite, 3 plus infinite. Next for vertex 4, 5 plus infinite, 5 minus 2, 3, 5 plus 0, 5, 5 plus infinite, 5 minus 1, 4, 5 plus infinite. Next for vertex 5, 3 infinites, then 5 plus 0, 5, 5 plus infinite, 5 plus 3, 8. Next for vertex 6, 4 plus infinite, then here 4 plus 0, 4, 4 plus 3, 7. Next for vertex 7, all infinites only we will. So this is a new cost matrix we got in third iteration by relaxing the edges k equal to 3. And from this, find the minimum value. So for vertex 2, which one is minimum we will consider. So minimum here if you are considering it is 1. For vertex 3, minimum value was 3. For vertex 4, minimum value was 5. For vertex 5, minimum value was 2. For vertex 6, minimum value was 4. And for vertex 7, minimum value was 7. So this is the new shortest distance from source vertex to all other vertices we got in iteration 3. So with this shortest path, we will continue the next iteration. So with this shortest distance, add with the corresponding cost matrix, we will get a new cost matrix again in fourth iteration. Okay. So 0 plus 6, 0 plus 5, 0 plus 5, 0 plus infinites. Okay. Next for vertex 2, 1 plus 0, 1, 1 plus infinite, 1 plus infinite, 1 minus 1, 0, infinite. For vertex 3, 3 minus 2, 1, 3 plus 0, 3, 3 plus infinite, 3 plus 1, 4, infinite, infinite. And for vertex 4, 5 plus infinite, that is infinite, 5 minus 2, 3, 5 plus 0, 5, 5 plus infinite, 5 minus 1, 4, 5 plus infinite. Next for vertex 2, 2 plus infinite. This is infinite, 2 plus 0, 2, 2 plus infinite, 2 plus 3 is 5. Next for vertex 6, 4 plus infinite. So 4 infinites we will get. 4 plus 0, 4, 4 plus 3, 7. Next is 7 plus. So here all infinites we will got. Only last column we will get 7. So this is the new cost matrix we got in fourth iteration. From this, we have to finalize the minimum value. So for vertex 2, minimum here is 1. For vertex 3, minimum here is 3. For vertex 4, minimum here is 5. For vertex 5, minimum is 0. And for vertex 6, minimum is 4. Vertex 7, minimum is 5. So this is the new shortest distance from source vertex to all other vertices we got. With this, continue the next iteration. Relaxing the edges k equal to 5. So this is the new shortest distance. Add with the corresponding cost matrix to get new cost matrix. 0 plus 6. This one is 0 actually. Okay. So 0 plus 6, 0 plus 5, 0 plus 5, 0 plus infinite. Next vertex 2, 1 plus 0, 1 plus infinite, 1 plus infinite, 1 minus 1 is 0, infinite, infinite. Next for vertex 3, 3 minus 2, 1, 3 plus 0, 3, 3 plus infinite, 3 plus 1, 4, 3 plus infinite, 3 plus infinite. For vertex 4, it is 5 plus infinite, infinite, 5 minus 2 is 3, 5 plus 0, 5, 5 plus infinite, 5 minus 1, 4, 5 plus infinite. Next for vertex 5, it is a mistake, it is 0, value is 0. So 0 plus infinite, infinite, 0 plus 0, it is 0, infinite, 0 plus 3, it is 3. Next for vertex 6, 4 plus infinite, and here it is 0 plus 4, 0 plus 3, 7. Next 5 plus, here all infinites we will get, only the last column we will get 0 plus 5, it is 5 we will get. So from this we need to find the minimum one. So for vertex 2, if you are considering, minimum value is 1. For vertex 3, minimum is 3. For vertex 4, minimum is 5. For vertex 5, minimum is 0. And for vertex 6, minimum is 4. For vertex 7, minimum is 3 now. Okay, so 1, 3, 5, 0, 4, 3. So this is the shortest distance we got at 5th iteration. So one more iteration, we need to relax the edges, that is n minus 1 times. Okay, so with the shortest distance, continue the next iteration. Add this new shortest distance with the corresponding cos matrix. So for vertex 1, it is 0 plus 6, 0 plus 5, 0 plus 5, 0 plus infinite. For vertex 2, 1 plus 0, 1, 1 plus infinite, 1 plus infinite, 1 minus 1, 0, infinite, infinite. For vertex 3, it is 3 minus 2, 1, 3 plus 0, 3, 3 plus infinite, 3 plus 1, 4, 3 plus infinite, 3 plus infinite. For vertex 4, it is 5 plus infinite, 5 minus 2, 3, 5 plus 0, 5, 5 plus infinite, 5 minus 1 is 4, 5 plus infinite. For vertex 5, it is 0, 0 plus infinite, 0 plus infinite, infinite, 0 plus 0, 0 plus infinite, 0 plus 3 is 3. And for vertex 6, it is 4 plus infinites. All infinites we will get, only last two columns, 4 plus 0, 4, 4 plus 3, 7. For vertex 7, 3 plus. Okay, so here all infinites we will get it, and 0 plus 3 we will get it 3. So from this find the minimum value. So for vertex 2, minimum is 1. For vertex 3, minimum is 3. For vertex 4, minimum is 5. For vertex 5, minimum is 0. For vertex 6, minimum is 4. And for vertex 7, minimum is 3. And if you are considering here, the previous iteration and this current iteration, we got the same shortest distance. Okay, that means we got the correct shortest distance from source vertex to all other vertices in the given graph. That is the meaning. Okay, that is last two iterations we need to get the same shortest distance. So now the final shortest distance we got in 6th iteration. That is n minus 1 times we need to relax the edges. That is 6 times we need to relax the edges. At the 6th iteration, we will get the shortest path from source vertex to all other vertices. Okay, so now we will implement the shortest distance what we got in each iteration. That is every time when we are relaxing the edges, what is the shortest distance we got, that we will fill it in this table. Initial distance we got in first iteration. The values are 0, 6, 5, 5, infinites. Okay, and when k equal to 2, that is relaxing the edges, k equal to 2, distance we got is 0, 3, 3, 5, 5, 4 and infinite. When k equal to 3, we got 0, 1, 3, 5, 2, 4, 7. When k equal to 4, the distance we got is 0, 1, 3, 5, 0, 4, 5. And when k equal to 5, we got is 0, 1, 3, 5, 0, 4, 3. And at the last iteration, we got is 0, 1, 3, 5, 0, 4, 3. The meaning here is, when we are implementing the last two iterations, the value should not change. Then that is the final shortest distance we got from source vertex to all other vertices. So here we are considering, in the sense, this is the source vertex, its distance is 0. Okay, shortest distance. So from 1 to 2, the shortest distance what we got here is 1. So how we are getting 5 minus 2 minus 2, we are getting 1. This is the shortest distance. Okay. Similarly, for 1 to 3, shortest distance is 3. That is 5 minus 2. And 1 to 4, shortest distances, we need to consider the directions also. So 1 to 4, shortest distance is 5. So this is the shortest distance. There is a direct path. And 1 to 5, if you are considering, shortest distance is 0. That is 1 to 4, 4 to 3, 3 to 2, and 2 to 5. We will get shortest distance 0. That is 5 minus 2 minus 2 minus 1. Similarly, for 1 to 6, shortest distance is 4, 5 minus 1. Okay, 1 to 7, shortest distance is 3. 1 to 4, 4 to 3, 3 to 2, and 2 to 5. And 5 to 7, we will get 3. Okay, so this is the shortest distance we got from source vertex to all other vertices in the given graph by implementing Bellman-Ford algorithm. Okay, so in Bellman-Ford algorithm, we need to remember two key points. One is we need to relax the edge n minus 1 times. So in every iteration, we will find the new shortest path. In the last iteration, what is the shortest path we got? That will be considered as the final shortest path. In every iteration, while calculating the shortest distance, we need to remember this formula. That is d of v is equal to minimum of d of v or d of u plus cost of u comma v. Here u will be considered as the source vertex and v will be considered as the destination vertex. So this formula we have to implement for every iteration to add the shortest distance cost plus the cost matrix, initial cost matrix value. Then we will get a new cost matrix in every iteration. With that, we will find the minimum value. So this is the procedure to implement Bellman-Ford algorithm. Thank you for watching this video.